Welcome to a new session on the massive open online course Introductory Concepts of Digital Computing offered by Swayam. In the last session, we discussed about different number systems, in particular binary. As we know, computers or any digital electronic devices represent all different types of data such as audio, video, text, etc. in binary numbers. So, to understand more about digital computing and digital systems, it is essential to know binary arithmetic. The different arithmetic operations are addition, subtraction, multiplication and division. In this session, we are going to learn binary addition and binary subtraction. From the last lecture, you may recall that the signed binary numbers can be represented in three different forms: signed magnitude form, 1's complement form and 2's complement form. The addition of two numbers in the signed magnitude form follows the rules of decimal addition. That is, if the sign of two numbers are same, then just add the numbers. If the sign are opposite, subtract smaller number from the larger number and the result will get the sign of the larger number. Consider 25 plus minus 39. Here we subtract 25 from 39 and we get 14 and give sign of 39, that is minus. So, the answer is minus 14. The same concepts are followed for binary addition too. So, we start with binary addition as it is the most important and easiest of all operations. The four rules of binary addition are 0 plus 0 equal to 0, a carry 0, 0 plus 1 is equal to 1 with a carry 0, 1 plus 0 equal to 1 with a carry 0, and the last case 1 plus 1 is equal to 0 with a carry 1. For the first three cases, it is similar to the decimal addition: 0 plus 0 equal to 0, 0 plus 1 equal to 1, 1 plus 0 equal to 1. But when the input A is 1 and B is 1, the sum is 1 0, where the 1 is considered as carry to the next level. For example, add two numbers 1 0 1 0 and 0 1 1 1. The bits of unit place are added. 0 plus 1 is equal to 1. Then the bits of place value 2 are added. 1 plus 1, which is equal to 1 0. That is, 0 is the sum and we get a carry 1. The carry is forwarded to the next left column. Now consider digits of place value 2 square or 4. Again, 1 plus 0 plus 1, which is equal to 0 with a carry 1. And finally, we add the most significant bits 1 and 0 with the carry forwarded from the previous level, that is 1 plus 0, which is equal to 1 0. So, the answer is 1 0 0 0 1. Let us try a similar problem with 8 bits: 1 0 1 1, 0 1 1 0 plus 1 1 0 0 0 1 1 1. In the least significant bit position, we have 0 and 1, which results in 1. Next, left column, 1 plus 1 equal to 0, we have a carry to the next column. Then it becomes 1 plus 1 plus 1, which is again 1 with a carry 1. So, in the next column we get 1 plus 0 plus 0, which is equal to 1. Next it is 1, next it is 1, and in the next 0 plus 1 equal to 1, and the most significant bit position 1 plus 1 is equal to 1 0. So, here carry is generated 3 times. Next, we are going to see how subtraction is performed in binary. The basic rules for subtraction are 0 minus 0 equal to 0, that is the difference, and the borrow is 0. 0 minus 1 is equal to 1. 1 is the difference and the borrow is 1. Because when you consider 0 minus 1, 1 is larger than 0. So, subtraction is not possible. So, we borrow 1, then it becomes 1 0 minus 1 and the result is 1. That is why we write 1 in the difference column and 1 in the borrow column. And the next row, 1 minus 0, which is equal to 1 with a borrow 0, and the last case 1 minus 1 equal to 0 and borrow also equal to 0. In subtraction, we may need to borrow 1 from the previous column. This happens when we subtract 1 from 0, that is 0 minus 1. When we borrow a 1 from the previous column, a 1 0 is created in the column being subtracted. And continue subtraction using the above given rules. Let's perform the binary subtraction 1101 minus 0011. In the first column, at units place, 1 minus 1 equal to 0. Then in the second column, perform 0 minus 1. But we cannot subtract 1 from 0, so borrow 1. When you borrow 1 from the column 3, the 1 at column 3 becomes 0 and 0 at column 2 becomes 1 0. Subtract now 1 0 minus 1, which is equal to 1. Next, column 3, 0 minus 0 equal to 0, and in column 4, 1 minus 0 equal to 1. Therefore, 1101 minus 0011 is equal to 1010. One more problem, 1010 minus 0111. In the first column, it is 0 minus 1. We need to borrow 1 from the second column that creates 1 0 in the first column and leaves a 0 in the second column. Then it becomes 1 0 minus 1. We get 1. In the second column, again 0 minus 1. But you cannot borrow from the previous column as there is no 1. So, we borrow from the column previous to that by leaving a 0 in the fourth column. Then 0 in the third column becomes 1 0. Now, we can borrow 1 from this 1 0 to second column. This makes a 1 in the third column and we get 1 0 in the second column. Then apply the rules of binary subtraction to complete the process. In the second column, 1 0 minus 1 equal to 1. In the third column, 1 minus 1 equal to 0, and in the last column, 0 minus 0 equal to 0. Hence, 1010 minus 0111 is equal to 0011. This method of subtraction works perfectly only when the minuend is greater than the subtrahend. So, we learned how addition and subtraction is performed in binary. The limitations of this approach is we need separate adder and subtractor circuits for addition and subtraction. If we are able to represent a negative number in its ones complement or twos complement form, we no longer need a subtractor circuit because subtraction can be done by using addition. For example, to subtract 12 minus 15, we just add 12 and minus 15. 12 plus minus 15, where minus 15 is in its twos complement form. Add them, we get the answer. This simplifies the circuit design to a great extent. We can use ones complement form instead twos complement, but we restrict the discussion to twos complement as it is the most common form of negative data representation. The next topic, binary subtraction using twos complement. How to perform subtraction using twos complement? Subtraction can be done by using addition. For example, subtracting 15 from 12, that is 12 minus 15, which is equal to 12 plus minus 15. So, to subtract a number, what do? change the sign of subtrahend and add it to the minuend. How to change the sign? By taking the 2's complement of the number. For example, take the 2's complement of 0, 0, 0, 0, 1, 1, 1, 0, that is plus 14. We get 1, 1, 1, 1, 0, 0, 1, 0, that is minus 14. When you evaluate the sum of weights, you will get this value. Check the value: minus 2 raised to 7 plus 2 raised to 6 plus 2 raised to 5 plus 2 raised to 4 plus 2 raised to 1, which is equal to minus 14. We have done this in a previous session. When we take the 2's complement of 1, 1, 1, 0, 1, 1, 0, 1, that is minus 19, we get 0, 0, 0, 1, 0, 0, 1, 1, that is plus 19. So, to subtract two signed numbers, we have to add the minuend and subtrahend by changing the sign of subtrahend. Discard if a carry is generated. We must also be watchful in the number of bits. It must be the same for both operands. So, the first step is to make sure that the number of bits in both subtrahend and minuend are equal. If not, add zeros to the left of the operand having less bits. Then change the sign of subtrahend and finally add with minuend. In general, if A is the minuend and B is the subtrahend, the subtraction takes place as plus or minus A minus plus B, which is equal to plus or minus A plus minus B. And the next, plus or minus A minus minus B is equal to plus or minus A plus plus B. Let's work out few problems on subtraction of signed numbers. Consider the first one, 20 minus 13. This can be written as 20 plus minus 13, which is equal to 7. Let's do it in binary. 0, 0, 0, 1, 0, 1, 0, 0 minus 0, 0, 0, 0, 1, 1, 0, 1. We have to change the sign of subtrahend and add. So, the expression becomes 0, 0, 0, 1, 0, 1, 0, 0 plus 2's complement of 0, 0, 0, 0, 1, 1, 0, 1, which is equal to 0, 0, 0, 1, 0, 1, 0, 0 plus 1, 1, 1, 1, 0, 0, 1, 1, which is equal to 0, 0, 0, 0, 0, 1, 1, 1, which is equivalent to plus 7. Note that the carry is discarded. The next problem, 22 minus minus 7, which is equal to 22 plus 7, that is 29. Let's do it in binary. 0, 0, 0, 1, 0, 1, 1, 0 minus 1, 1, 1, 1, 1, 0, 0, 1, that is equal to 0, 0, 0, 1, 0, 1, 1, 0 plus 2's complement of subtrahend, which is equal to 0, 0, 0, 1, 0, 1, 1, 0 plus 0, 0, 0, 0, 0, 1, 1, 1. And the result is 0, 0, 0, 1, 1, 1, 0, 1, that is equal to plus 29. And the third problem is minus 16 minus plus 7, which is equal to minus 16 plus minus 7 equal to minus 23. Let's try it in binary. The binary equivalent of minus 16 is 1, 1, 1, 0, 0, 0, 0. So, the problem is 1, 1, 1, 0, 0, 0, 0 minus 0, 0, 0, 0, 0, 1, 1, 1, which is equal to 1, 1, 1, 0, 0, 0, 0 plus 2's complement of 0, 0, 0, 0, 0, 1, 1, 1, which is equal to 1, 1, 1, 0, 0, 0, 0 plus 1, 1, 1, 1, 1, 0, 0, 1. Do the binary addition. We get the answer as 1, 1, 1, 0, 1, 0, 0, 1 equal to minus 23. Here also the carry is discarded. Let's do one more problem where both the operands are negative. Consider minus 18 minus minus 6. Here the operands, first operand minus 18, second operand minus 6, both are negative, and the result is minus 18 plus 6 is equal to minus 12. Let's do it in binary. 1110, 1110, that is the binary equivalent of minus 18, minus 11111010, that is the binary equivalent of minus 6, and this is equal to 11101110 plus 2's complement of 11111010, which is equal to 11101110 plus 00000110, and in turn it is equal to 11110100, which is equal to minus 12, or the result is shown in its 2's complement form. If the digital device stores all the numbers in 2's complement form, then there is no need of subtraction. Just adder circuits are enough to perform both addition and subtraction. Let's move on to the last topic. Here we are going to discuss overflow. What is overflow condition? The range of values that can be represented in signed 2's complement form is minus 2 raised to n minus 1 to plus 2 raised to n minus 1 minus 1. When the result of an arithmetic operation of numbers represented in signed 2's complement goes out of this range, an overflow occurs. Or when the allowed number of bits are insufficient to store the result, an overflow occurs. For example, consider 3 plus 6 in 4-bit signed 2's complement. It is 0011 plus 0110, and the result is 1001. We added two positive numbers, but in the result there is a 1 in the sign bit, means that it is a negative number. So the sign is incorrect. Magnitude also differs. Actually, 3 bits were sufficient to represent the numbers 3 and 6. 4th bit is the sign bit, but 4 bits were required to store the result. This is a case of overflow. If the sign bit of the result is different from the sign bit of operands, then that is an indication of overflow. Overflow can also be detected by checking the carry in carry out at MSB. If C in not equal to C out, that also indicates overflow. For example, consider 7 plus 6 in 4-bit signed 2's complement representation. 0111 plus 0110, which gives you the answer as 1101. In this example, carry in at MSB is 1 and carry out is 0. It is an indication of overflow. An overflow occurs only when both the numbers are positive or both are negative. Otherwise, it will not go out of the range. So, we have come to an end of the session. Let me summarize the topics we discussed. The addition and subtraction of binary numbers are similar to decimal numbers. Addition on positive numbers can be performed just by following the rules. But for negative numbers, we have different representations, and for subtraction, we have alternative methods too. Binary subtraction using 2's complement form was well explained. Also, we had a discussion on overflow. The remaining two operations, binary multiplication and division, will be handled in the next class. Thank you for watching. See you in the next session. Bye.